So let's continue from the point where we stopped yesterday. Do you have any questions with respect to the problem that we solved? Is everything clear? Good. So, next thing. Same stuff, but in logarithmic scale. Do you remember what was the term here? It was at least part of it is the phase transmission equation. And when we expand the multipliers, 4 pi, 10 on 6, 10 on 10, we can separate this as a constant. And when we take, when we transfer this to decibels, this came as numbers, and losses between 2 points, free space propagation loss, became this expression. So we can either work with linear scale, and which is more logical and close to the physics, or use this short expression. We just have to put the frequency in megahertz and the distance in kilometers, and this equation will spit out the loss between 2 points for a given frequency and given distance. So it's just an engineering trick to make our life easy. It's not a rocket science. The point is to get used to decibels, that's all. I won't bother you with that. We'll just show you an example. A ground-based communication system transmits toward a geosynchronous satellite. Many of you know that geosatellites are located on geostationary orbit, which is about 40,000 kilometers apart from Earth. And let's assume 1 gigahertz of the transmission frequency. The gain of ground-based antenna is 2 dBi, and the satellite has a smaller antenna with a gain of 15 dBi. So the setup will look something like that. This is the Earth. This is the geostationary orbit, approximately 6 Earth radii. This antenna has a gain of 25 dBi. What was the I stands for?
Compared to the isotrope.
Exactly, compared to the isotropic radiator. And the satellite antenna, 15 dBi. What must be the transmitted power? P transmit equals to question mark to produce 5 microvolts root mean square over load of 50 ohms. Why the problem is positioned like that? Because we know the sensitivity of the receiver. So we think that 5 microvolts on its input will produce enough signal to noise ratio so the signal will be detectable. In other words, we are putting a receiver on a satellite. We know where the satellite is and we would like to know how much power we need to transmit in order to close the link. Can you solve it for yourself?
This is the resistance at the bottom of the text, right? 50 ohms.
Yes, it is the input impedance of the receiver. I will give you a hint. Knowing the input impedance of the receiver and knowing the voltage that needs to be produced, we can calculate the power that we need to deliver to this input in order to produce this voltage. You know, power, impedance, and voltage are connected. A1 ready or almost ready.
Can you show the previous slide for a second?
This is how to estimate the free space loss.
Can I add something?
Yes.
The equation, the second P, is the power of the transmitter
Here,
inside the equation. So,
inside, which one?
so there is written that the power of receiver is equal to power of the transmitter.
Mm-hmm.
Okay.
This is valid assuming gain of antenna of unit or 0 dBi. So the antenna gain is not included in this equation. You just have plotted here. G transmit in decibels plus G receive in decibels. That's all.
I have a question. So if you have the distances in kilometers and the gain in decibels, the units are what's on the end that we're trying to find. The power.
Units.
The measuring units.
You get the ratio.
Uh-huh.
You get the ratio between. So you have to convert. First, the approach should be like that. First, you estimate what will be the power needed to on the input of the transmitter, based on the sensitivity, the required voltage, and the impedance of the input. Then you convert this power to dBms, decibels against 1 milliwatt, and then you add all the losses, and then you will receive the power needed to be transmitted. Is somebody ready with the answer?
Excuse me, could I ask about the value of the distance r and also the frequency?
Forty 42,000 kilometers approximately, 1 gigahertz, 5 microvolts per minute. Are you give up?
Can you explain how we can find the power of the transmitter?
Easy. First of all, you have a 50 ohm matched load. What means matched load? It means the whole transmission or receive path is matched to that 50 ohm. So we will no reflection loss from the load. This is the input impedance of the receiver. So how much power P receive needs to enter in order to produce here 5 microvolts. How much power?
Ten.
Hmm?
10.
How do you calculate?
So the
We know from the electricity that if we have a resistor, an impedance, and current that flows through the resistor is I, we have a voltage drop V, and this is R, the impedance, and we have power that will be delivered to the load P. And what is the relation between?
The voltage to the second power divided by the impedance.
Yes, absolutely. Easy. Basic electrotechnics. P equals either voltage drop squared over the load, either current passing through the resistor squared times the impedance. And we can estimate the power. How much should be that?
Is the resistance 50 ohm?
Yes.
Okay.
This is standard impedance of any instrumentation. The 99% of them are made to have input impedance of 50 ohms for many reasons. The other standard is 75 ohm, the other standard is 100. Actually, this should be studied into the physics class on the 8th grade, so maybe 7th grade to the high school. Maybe. At least when I was schoolboy, that was the case. Where are you from? Good with electricity? So don't touch a screwdriver. Yes?
Yes.
What is the answer?
It's not dry.
You're almost there.
But I'm confused.
Why?
I'm not sure what to do.
This is correct. So you put the voltage here, convert it in volts, and then do the math, and then convert it in milliwatt, and then you're fine.
Okay.
If you are not sure what units to use, always work in fundamental units. Volts, watts, ohms. So we convert this 5 microvolts to 5 times 10 on power minus 6. And then we divide it by impedance, 50, and then this will be the answer in watts. And to convert it in milliwatts, divide it by 1000, multiplied by 1000, and then take 10 times logarithm of the value. And we receive the power. This shouldn't be that correct.
I'm not sure how to do the conversion in decibels. Can you explain how?
What's the difference between the first and second line other than the units in watts and milliwatts?
Here the notation is decibels. It should be dB watts. Decibels against 1 watt. And here is decibels against 1 milliwatt. And here we put the power in watts, and here we put the power in milliwatts. That's the difference. So this is used everywhere, and this is used mainly in the Earth station design and techniques. dB is pretty large amount of power. dBm is something within our everyday things. Minus 60 dBms are very small, and plus 60 dBms are relatively high power, but within our everyday reach. For instance, the wireless router transmits about 20 dBms, 100 milliwatts. Did someone get to the solution? Or at least partially to the solution?
Almost.
Do you need more time, or you can report it?
I'm reading it right, 1.8 dB watts.
For the power needed on the input of the receiver, or for the transmit power?
The transmit power.
It's too low. Okay, I will tell you the answer so we can continue. Here is it. First, power received equals to voltage squared over the impedance of the input, which means 5 times 10 on minus 13 watts. And to convert it to dBm, we divide this to 1000, and then take a logarithm, and we get minus 93 dBms must enter the input of the receiver. And now one question for top-notch professionals. Why the condition says 5 volts root mean square instead of 5 volts?
Because you're going to be working with AC current. AC
The-
voltage.
This both can apply to AC current, but there is a slight difference between 5 volts and 5 volts RMS. Because sinusoidal current changes along the zero line. Plus, and if we get this peak here, we say 5 volts. The peak value. However, if we connect it to the 1 ohm impedance, it then gonna produce 5 volts squared over 1 ohm power. And it will produce less power. And how much less?
0.7 times
Squared.
squared.
It will produce not 5 volts over 1 ohm, but effective value, which is 5 volts over square root of 2. This is so-called effective value of the sinusoidal current. If the current is not sinusoidal but something else, effective value will be different. So we have to take a square root of this and multiply it by square root of 2 squared, and we will get 12.5 watts over a resistor of 1 ohm. And that's why when they say 5 volts RMS, here we assume that we have already this root mean square value, not this one, not the peak value. Not the peak value. Okay, so I guess up to this point everything is clear. We need minus 93 dBms to enter the receiver in order to produce this 5 microvolts. Fine. And then we add the gain of the receive antenna, which is 15 dBi, and then we add this number. What is this number?
Loss.
Yes, free space path loss, which is calculated by this equation. And then we add the gain of the transmitter antenna. And just assuming all these numbers, we get plus 52 dBms, which is 32 dB watts, and once we convert it to watts, we get 158 watts we have to transmit in order to get this small power on geostationary orbits. Everything in this world works in this manner. Everything.
I want to ask, so we sum up these things, they are measured in decibels, and we get result in decibels, decibel milliwatt, right?
Right.
So what's up with the units?
You get minus 52 dBm, and you can convert easily to milliwatts because the difference between dBm and dBwatt is 30 decibels. So you just subtract 30 from this, you will get 32 dB watts, and then you can easily convert it to watts. 32 dB watts means that 10 on power 32 over 10 watts. Easy peasy. Easy peasy. Oh, sorry, my bad. 22. 52 minus 30 is 22. My bad. Okay, very good. Is everything clear so far? Now we what antennas are, how they work, what the gain is, and how they transfer power one to another. Here is example of with a wireless router, but we ain't gonna solve it because it's basically the same thing, but the same thing with for different scenario. There is no point to spend time on that. Here is more interesting thing. Radar equation and radar cross section. What does that mean? It means we transmit signal, it has the target, get the transmitted back, and get received from the radar antenna. The receive antenna could be the same as transmit antenna, or could be different antenna. So this is called monostatic scenario, bistatic scenario. And what is specific about this thing? Pretty much the same as Freeze transmission equation. We just have to apply it 2 times for ongoing and upcoming path. It means that the received power will depends 2 times on the path. So it will be, the loss will be not on power of 2, but the power of 4. That's why detecting things with radar is so hard, because the power decrease with the 4th power of the distance.
those angles that they're written there, where do we measure them?
These angles are angles of direction of the radar. Because sometimes
Yeah.
the target is not toward the peak of the antenna, it's on a side. This angle tells us that we have to use the power pattern of the antenna in order to calculate how much power we transmit toward the
And
antenna.
on this scheme, which one is?
Well, it's not so important. It's just important to keep in mind not to use the peak gain of the antenna, but the gain that is applicable to the direction, specific direction. In ideal case, this will be the peak gain of transmit antenna, peak gain of the receive antenna. But in real time, it's not so easy to pick the target. So let's say instead of 20 decibels of gain, we will get 15 decibels of gain. This is the important one. In an ideal case, antenna will pick the target, point the target, and we use the maximum gain of the antenna. But this rarely happens. And then one more thing, which is highly interesting, so-called sigma or radar cross-section of the target. This is the effective area that actually reflects the signal back. And human has effective area of 1 square meter. So human is equivalent of piece of metal sheet with size of 1 square meter. Different things have different radar cross section. And here is an example of what has what cross section. For instance, strategic bomber has 100 square meter of radar cross section. It's pretty large, pretty well visible on a radar. Blackjack, it's a bomber. In American denomination, B is bomber, F is fighter. A is assault something.
Plane.
Plane. In Bulgarian се нарича штурмови самолет. Russians don't have such designation, so you have to know which number means what. And here, so you see fighters, yes, they have a much lower radar cross section compared to the bombers. And here you can see how the stealth technology came into place. So B1B has less than a human radar cross section. And it's still pretty large aircraft. This, of course, is applicable to specific frequency ranges, where the shape of the plane and the cover is made to absorb or scatter the waves. So not all the range of frequencies is absorbed or scattered. Just there where you can expect that enemy is employing the radars. That's how we designed the aircraft. And F-117 is almost invisible to radars in a specific frequency range. But that's why smart people develop broadband radars, and you expect that target will be lighted up
In frequency.
in some frequency. Or use multi-static radar, because if the shape of the plane scatters the waves toward other direction, not toward direction of the main radar, you can see it, but from another location, see, oh, this guy is there. Yeah. Nice temperature. What is nice temperature?
The
Very
higher,
bad thing.
the higher the temperature, the higher the noise.
Yes, something like that. Noise temperature is something that is a part of our life, and the thing that actually impairs the communication link. In low frequencies, let's say kilohertz, something there is no much of a noise, natural noise. However, going up with the frequency, noises start to pop up from somewhere, and we are wondering where they are coming from. And the first thing to know is that every conductor that has a resistance, and a resistance have everything except superconductors, produces, due to chaotic movement of electrons inside, a voltage on its clumps. So if you get a 50 ohm resistor and measure it with highly precise voltmeter, you will see a voltage with a random shape and waving around a specific value. And we wonder how to measure this value. Very easy. Smart guys have done this before us. If we connect this voltage source to a matched load, it means our 50 ohm noise source. We call it noise because it's a random voltage, not a signal like sinusoidal voltage. Connected to the matched load, the 50 ohms, noiseless, we'll see that our load is seeing a specific power. And this power is equal to Boltzmann constant, the physical absolute temperature of the body, times the frequency bandwidth that we are looking for. So these three things, knowing the temperature, we can estimate how much power we will receive, noise power we will receive just due to the finite temperature of the body. This is first source. Of the noises. And can you tell me the second source? Can you tell me the second source? Astronomers? Yes.
Second source of temperature noise.
Yes.
Yeah.
It's using it in the medium.
Well, if there is a rainy day, yes. But here we get the parabolic dish pointed to the sky.
Yeah, the microwave.
Cosmic microwave background.
Big Bang noise
This
explosion
and that.
radiation.
And the sky is noisy also. It's not completely zero, something is coming from the sky. It is well described in the literature as tables and graphs relative to the angle. We receive something from the sky, from the galaxy, even not pointing antenna to a large source like a moon or sun. The sun is enormous also now. But even if you point antenna toward the sky, we receive some noise, and this noise adds here. And on top of it, if antenna is pointed to the, let's say, a star, antenna is still on the ground, and part of the pattern will see the hot ground and receive noises
From the ground.
from the ground, and with back lobes also.
Yeah.
So all these three things sum up as a noise power, which can be expressed with that noise temperature. And we say we are monitoring a bandwidth of 1 megahertz, and our antenna see that power, and that power will be expressed as a noise temperature. We say antenna is hot 20 kelvins, or antenna is hot 30 kelvins. And why we do care about that? We do care because the signals that we are receiving from a galaxy far, far away is compared to that noise. Even microscopic noise, it's barely noticeable with highly sensitive equipment. The problem is that the signals that we are aiming to are also comparable with that noise or even less. And if we divide the gain of the antenna to the temperature, noise temperature that this antenna actually exhibits, we call it figure of merit of the antenna, or G over T. And if you buy an antenna for your radio telescope, yes, that's the name, figure of merit. If you decide to buy an antenna, you should know what is antenna's G over T. Not only gain, but also what noise it's like buying tomatoes from the shop. If you want to make a good shopska salad, you need good tomatoes. Not only big tomatoes, but also high quality tomatoes.
Yeah.
Otherwise the salad will be spoiled.
So how do we fight this noise? How do we reduce it? Do we narrow the frequency band?
Yes, but we want to see a large band, so this is ain't gonna work. There is one way, two ways actually. First way is to apply cryogenic techniques. So artificially decrease the own temperature of the antenna.
Yeah.
Cooling, yes.
Yeah.
Cooling.
Like the CCD cameras.
Exactly.
Yeah.
There is nothing new under the sun. Cooling, and the second one is to minimize the side lobes by designing high quality antenna so it doesn't see the noise sources. Well, so you see, if we have a simple communication from here to there, like a wireless router, we don't care about these things. If you want to make highly sophisticated antenna, a receive system, then we deal with enormous amount of problems. Good. For a home satellite antenna, typical GRT value is about 13 decibels. About 13. 1, 3. For radio astronomy antenna, large antenna reflector, maybe 25, 30, 40,
300.
300 could be. If you want to communicate with Mars, Mars is really far away. We need a large antenna with cryogenic amplifier. Not only because Mars is far away, but also because the probes sent there has very limited power and very small antennas.
But isn't it more sense to communicate with satellite in orbit, and after that the satellite to communicate to the ground station on the Earth
Yes.
to reduce the noise of the Earth?
The problem is when satellite looks toward the ground station on the Earth, it sees also the hot Earth.
Yeah.
So immediately its noise temperature rises up, and it's this
But you can increase the power
from where? From ground?
from the satellite.
Well, for reception, there is no way to increase the power. You rely on the transmit power of the ground.
Yeah.
Now, all these problems are solvable, but you have to sacrifice something.
Yeah.
And it's up to the engineer to decide what to slash and what to give priority. And this is, I didn't translate it anyway. Communication and budget is when we add all the power coming from the transmitter and the receive, and then we add all the noises that we already spoke about, KT and frequency bandwidth, and when we divide these two, we receive carrier to noise ratio. And this is what actually does our job. C2N, carrier to noise ratio. Power of the useful signal divided to the power of noises generated in antenna, received through the pattern, or generated in the active devices of the. Usually, the first stage is the most, not usually, but the first stage of the amplifier is the essential to the noise of the receiver. C2N or C over N, C2N ratio or C over N or C2N, different ways to say carrier to noise. Good. Very good. Any questions about the communication budget? Only remark, sometimes the useful power, the power that we want to use and detect is known. We know we have a carrier. Human-made carriers are easy to detect because we expect something. We know what to expect.
You know the PT, the transmitter.
Yes. If we aim to something that we don't know, then problems arise, like looking at the sun and try to detect some electromagnetic emission. We receive something, but we don't know if what we see is the transmission from the ionosphere, let's say, or just noise that happens in our receiver.
Yeah.
What are those coefficients before the received power in useful way? Yeah.
Oh, I don't know. I didn't know what I read. Sorry. Just forget it. It's not that important. This is important. P, and it's right here. D. Let me think about it. It is perhaps receive power reduced by some losses in the waveguides or something like that. So this is smaller by the power to the detector means. So this is power received in the antenna on the antenna flange, and then we have some additional losses like waveguide losses, cable losses. So the power decrease even more. So that's the main. Other things? Everything is picture clear, and I guess now you can close the communication link. And now we continue with some other properties of the antennas. Нещо международно.
Така.
Yes. Hey Valerio, how are you? I'm in a let's say seminar. Will it be possible to call you within an hour or so? Okay, let's do this. Once you land it, just give me a call. Okay. Yes. Okay. Thank you, and have a safe flight. Bye bye. Sorry, guys. Radiation resistance and input impedance. This is only applicable to wire antennas, not applicable to aperture antennas. What is this text? One of them is artificial, the radiation resistance, and the other is quite real. So, if we have antenna and connect it to a cable, it starts to transmit. And if we pretend that we are the current flowing inside this cable, what we gonna see? We flow here, and we get to the antenna terminal, and we see some resistance. Somebody is opposing to us to flow. And regardless the fact that the antenna is going somewhere in the air, like a cable waving around, for this wireless router, for example, the current here and the voltage here on the terminal will see a resistance, an impedance, right? Right.
Yeah.
And this impedance is called
Input.
input impedance of the antenna.
Because there is a different material.
I will tell you because. Because antenna radiates some power into the space. Right? Right.
Yeah.
Where this power is coming from? This power is coming from the cable.
Yes.
So in point of view of the cable, antenna is a load.
Yes. Okay.
The cable doesn't care whether antenna dissipates the power into the space or converts it to a heat. For point of view of the cable, this is power that's coming into the antenna. So, from point of view of the antenna, the power is consumed, from point of view of the cable, the power is consumed into the antenna. The cable doesn't care, the current in the cable doesn't care if this power is transmitted into the open space or consumed as a heat. So the power, and from our engineering point of view, this power consumed from the cable, we can divide it to two parts. One part is the power that is radiated into the space, what actually do our job. And the second part, inevitably connected to the antenna material, is the lost power which is consumed to do the finite conductivity of the conductors. So it's a lost power. These two powers, they have equivalent impedances. So we can represent them as loads. This load consumes the radiated power, and this load consumes the lost power. And the first portion we call radiation resistance of the antenna, and the second we call ohmic resistance of the antenna. So the input impedance consists of two parts: radiation resistance and ohmic resistance. From the point of view of the cable, the generator, we see both two. We don't know what the ratio is. But we don't care. If we design a generator or transmitter, we say antenna has an input impedance of 50 ohms, period. We don't care what happened with that power.
Okay.
And once we start to make the communication budget, we start to care, 1 watt is coming, but how much will be emitted?
Yeah.
And then radiation resistance comes to place.
Can we full screen the presentation? Some letters are very small and hard.
Yes, absolutely. And then, even more, if the antenna is not perfectly designed, we have a reactive component which represents the energy going from antenna to the source and back. Reactive energy, reactive power, which represents the reactive component of the input resistance. So, the input impedance of the antenna, sum of actually three things: the radiation resistance, the loss resistance, the ohmic resistance, and the reactive component. Yes.
Why is there a factor of 1/2 in front of in this formula for the power?
We already discussed it
Oh,
because if we assume the peak voltage, then we have to,
okay.
or peak current, we have to get.
Yeah, this is 1 over square root of
Yes,
2,
exactly.
which is in the
If we
current.
work with the effective value of the current, then won't be 1 over.
Yeah, okay.
So basically, the antenna is either a resonator or radiator.
It's a resonator, and moment of resonance, it gives you this impedance. So it's a loosely coupled resonator with the free space. A resonator that consumes energy. And it virtually consumes because it radiates. But from point of view of the source, it consumes it. And you will say, why do we care about the radiation resistance? We do care because for antennas which are shorter than a wave, radiation resistance is very small, like antennas for VLF, LF, low frequencies. Long wave antennas, they have very low radiation resistance, typically 1-2 ohms. And respectively, if the radiation resistance is low, antenna ain't gonna to transmit very much or ain't gonna receive very much. And the problem is, in the past, it was a problem of communications. We hardly broadcast anything. And now pretty much nothing is broadcasted to the low frequency, but they are very interested from point of view of astronomy. So it's not a problem to one guys anymore, but a problem to other guys. Okay, so radiation resistance is clear, I guess. And now, dipoles. Since our LOFAR telescope is built on dipoles, we want to know what the dipole performance looks like. And that's what the dipole performance looks like. On the abscissor, we have the ratio between the dipole length compared to the wavelength, and on the y-axis we have the impedance, which is a complex number. So sorry guys, in electricity we have complex numbers. So what we can see on this picture, we see that if the dipole is very small, very short compared to the wavelength, the active component of the input impedance is how much? 0. So it basically doesn't work. That's why very short antenna doesn't transmit. Input impedance is low, radiation resistance is low, it means that nothing goes to the free space. We start to increase the length of the arms, and some impedance starts to show up. And also, we see that reactive component of the input impedance starts to decrease. Initially, it is equivalent to a capacitor, and then on a point of almost 0.25 of the arm,
Lambda over 4.
yes, of the arm, or lambda over 2 for the whole length of the dipole, the reactive component is 0, and the real component is something, about 75 ohms. And we have found a sweet point where we want to be. having an active component only. And that's why most of the coax cables are built with input impedance 75 ohms or 50 ohms, because they are very close to the input impedance of the dipole. So you don't have to make complex matching networks. And if we go up with the frequency, input impedance rises dramatically. The reactive component rises dramatically, and about almost wavelength, we have second null of the reactive component. So the dipole again starts to resonate. It has input impedance of about 3, 4, 500 ohms. And you will ask why we don't use this to work, and we work on a half-wave dipole.
Because the antenna will heat up very much.
Yes. Because?
The antenna will heat up.
Because we will need more power.
Now you understand why antenna are not straightforward thing. It will have a very nice impedance, 2, 3, 400 ohms, which is realizable with a cable. It's not something that we cannot make, especially with a
Small distance.
the symmetric cable. Easy to make. Zero of reactive components, very nice. That's what we would like to see. However, if we have a full-length dipole, here we have, let's say, 300 ohms, good. We have a current distribution, something like this guy, and that guy, which is highly different from the current distribution if we have a half-length dipole. And what is the deal here? The deal here,
In the first case, we couldn't transmit power.
we could, but this current distribution will produce an ugly pattern. Pattern that is not pointed to one direction, but is spread around. So we say we don't want to work with this ugly radiation pattern because we don't have enough gain. And some people still use it. If you have here 5/8 of a lambda antennas, only for vertical dipoles, when you work with the reflection in the metal ground. Sometimes it's used, but only in this case. 5/8 lambda over metal ground. If we want to design Ayagi, it ain't gonna work as you would like. Just solely because of the current distribution. In the afternoon, we will work with the simulator, and at home you can, or even here, we can create a lambda dipole, full wave dipole, and see what the pattern will look like.
Do we compensate with like a waveguide or something?
No, physics. We cannot read it. Nice impedance, 0. Reactive component, but we cannot find it. And that's why the further resonances are also not used, because the current distribution is bad. We cannot use it. And the final thoughts, how the ground impacts the antenna. This is how. If we have a vertical dipole over the ground surface with several antenna heights above the ground, here is one perfectly put around the ground and then elevated. You can see this is the perfect picture. This is start to degrade the pattern, and then we have even more elevated dipoles, and antenna pattern. The antenna pattern splits because the direct signal from the antenna interferes with the reflected from the ground, and they create this ugly simply the pattern, antenna pattern deteriorates. You have zeros in the direction that you want some transmission, and something that is not good, but part of the life. And with horizontal dipole, they never work very well over the ground, with one exception. In our case, for radio astronomy, since the target is above, not on the ground level, this concept works. So in general case, if we need it for broadcast, horizontal dipole is a bad thing. But in our case, since our target is always on top, somewhere in the sky, the deterioration due to the finite ground conductivity is not a bad thing.
It's actually better because we don't have reflection from.
Yes. And the last thing for today, for this morning, is the mutual impedance of the antennas. Here is the example is with one active element and several passive elements. But this is valid for antenna arrays when we have a set of many active elements. So what this picture tells us, we have two elements here and here, and they will be electromagnetically coupled. So the reaction, the currents flowing in the parasitic element, the electrode in this case, will induce currents into the driving element. And the driving element will see like impedance that is imported from the adjacent element. And smart people calculate what will be the impedance, this mutual impedance due to mutual coupling, and created nice tables where you can calculate the eigenvalue, which is very good. The problem is, if you have system more complex than one driver and one coupled element, the problem became extremely complex. So in the past, many assistant professors worked to calculate a single AI. And nowadays, with the software that we installed yesterday, we can calculate this mutual coupling in seconds. Bang, 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 and you're there. And then you tell, optimize please my driving element to 50 ohm impedance, bam, 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 and in 10 minutes we have a solution. Calculating mutual coupling by hand is impossible task if you have more than 3 or 4 elements. But with computer power, it does the same like what humans do, but a million times faster. And simply brute force the task. Which is good. I love that. Just write the proper initial conditions, click run, and go home. And when you come in the morning, you have a solution. Present it and done. Yeah. And you will do this in the afternoon. And now let's make 15 minutes break and then we go to do some laboratory exercises.